And let me continue my lectures devoted to the modeling on linear polymers. Last time we discussed that we will try to model a long linear polymer molecule as an image of the smooth curve under the random mapping in order to get the smooth random curve which can change its topological type and which can get arbitrary topological type with positive probability. So my aim today is to present you such construction and discuss the properties of obtained random. Let me raise my screen. Here is my screen. I hope it is visible. And let's start. Okay, so today we will construct a stationary random node. As we said last time, and as I repeated today, we will get this random node as an image of some smooth curve in the space under the random map. So one can imagine that if we will move this smooth curve, then we will get moving random node. To do this, let me present firstly more motion of the curve in the space R3. We will do this from the simple linear equation with interaction. Let me describe. So suppose that A is a generator of the unitary semigroup in R3. One can just recall for herself or himself that A can be like generator of rotation in R2. So U indexed by T is a semigroup of unitary operators, linear operators which preserve distances in R3. Also suppose that WT is standard Wiener process in R3. Now consider the following simple equation with interaction. I just consider a linear equation with the noise. Here in the right hand side, you see interesting new term, MT. Here MT is a center of mass of our system. You can check that our equation describes the motion of every particle which start from the R3. You see x0u is equal to u belongs to R3. Mu t is an image of the initial mass distribution. And we consider the equation where in the right-hand side we have a dependence from our mass distribution ut, but very simple, just through center of the mass. Here, initial measure mu0 is supposed to have finite second moment. This equation can be solved easily if we just integrate it again over measure ut, right-hand side and left-hand side. Then we got the equation like dmt equal dwt, from where one can conclude that the center of the mass of our measure evolve accordingly to initial Wiener process. And then trivially one can consider the equation for the difference dx ut minus mt and get the representation for x ut. So one can conclude that under this equation, the center of mass is floating in R3 like Brownian particle, and measure is whirling around this this center of the mass. You see on the example a picture for the initial measure mu0, which was concentrated in three heavy points. I just marked by red the direction to these points from the center of the mass. You see that center of the mass is floating around R3, and we just have some rotation around the center. If mu is a visitation measure of smooth closed curve gamma 0 in R3, which is parameterized by the function f0 twicely continuously differentiable, it means that mu0 is defined as a Lebesgue measure of such S that F0S belong to set delta, then mu t will be a visitation measure of the new curve gamma t, which is just image of the initial. In this way, we define the motion of the curve in the space. But this motion is very simple. As it was mentioned before, the curve gamma t is rotated around its center of the mass, which can be calculated with the help of the parameterization. So the picture is like following. We have some curve gamma, and it evolves in the space, just rotating around the center, its center of the mass, and center of the mass is persisting Brownian motion in R3. What is important? During this motion, the curve does not change its topological type. It's evident. Why? Let us come back and see. Gamma t is an image of gamma 0, is an image, let me emphasize this, is an image of gamma 0 under the mapping X. But we can see that mapping X is a solution to differential equation. Let me emphasize initial differential equation. Despite of that it is a stochastic differential equation with dw in the right hand side, one can imagine that it has properties which are usual for solution to differential equation, namely the solution to good differential equation defines the flow of diffeomorphism. So if two points were distinct in initial moment of the time, they remains to be distinct at all the moments of the time. So our curve cannot interchange itself, it cannot cross itself, and then it cannot change its topological type. But with the help of this gamma t, we will define a new random curves, which is a subject of our interest today. Let me recall you that last time we stopped discussing the random field in R3, which is isotropic stationary random field consisting of independent coordinates, and every coordinate of this field is Gaussian random field with covariance. One can put here some multipliers alpha. Popular is 1/2, which we did last time, but it does not necessary to do it now. So we just have such covariance for our coordinates of random fields. We suppose that they are Gaussian and centered. Due to this, one can conclude using the Kolmogorov condition that our random field has smooth realization. Its realizations are infinitely many times differentiable on R3. Now introduce new random curve, which is just image of our gamma t under the mapping sign. What I am claiming that this simple construction give us the following interesting properties. Gamma t is a smooth closed random curve without self-intersection, and gamma t can have arbitrary topological type with positive probability. We will discuss these properties later. Now let's see that gamma t is stationary. Namely, this process psi ft is a stationary random process in the space CP. Idea of proof is the following. The curve gamma t is moved by the mapping we just discussed. Since MT, the center of the mass of our curve, is moving like WT, and then we can think about the representation of the solution in the different moments of the time. So one can check that the difference between values of the solution different moments of the time consisting of some deterministic expression here is it and some increment of the Wiener process. From this point of view, one can check that this increment can be represented as follows. You can see as follows. And now let me recall you that US minus 1 applied to inner process W is again process because US is a S is fixed and US is unitary operator. So the covariance using the covariance function of psi is invariant under rotation, then we get the stationary. Next step is that gamma t has mixing property. Namely, for square integrable functionals f in J from gamma t, the expectation of EF here is J from gamma t tends to expectation of f multiplied expectation on G. We have examples of such property, very simple, when we consider a sequence of independent equidistributed random variables. You remember that for independent random variables, we already have very nice property that expectation of the product is equal to the product of expectation. And you remember that for the sequence of independent equidistributed random variables, we have the law of large numbers, namely the average of its values, of its first n values, goes to expectation. Actually, the mixing property is more general condition which guarantees the same. And we will use it as follows. We will say, okay, our random node gamma t has mixing property. So in average, its topological characteristic must tend to the expectation of such characteristic from gamma zero, gamma capital zero. So this is a technical statement which will give us possibility to make some conclusions about the limiting behavior of topological characteristic of obtained random node. Since it is technical, I just give the idea of the proof, and the idea is the following. Excuse me. Павел Соломонович, у меня сейчас лекция, я перезвоню. Да. Я перезвоню. So, the idea of the proof is the following. Suppose that we have two jointly Gaussian standard normal variables such that we have the expectation of the product equal to alpha. So they are correlated. Then it occurs that for Hermite polynomials from these Gaussian random variables, the very nice formula take place. The expectation of the product of two Hermite polynomials from eta 1 and eta 2 is equal the product of k factorial delta km alpha k. Explanation is also not too hard to understand. It occurs that conditional expectation of hm eta 2 with respect to eta 1 is equal to alpha m hm eta 1. By the way, this is a very simple but important partial case of the definition of so-called second quantization for Gaussian random functions. For our simple case, when we have psi1 from Wt, we have the following representation. Suppose it is hk psi1 Wt1, and j zeta s is beta k hk psi1 Wt2. Then just conditioning with respect to Wt1, we get the following representation for expectation. Here we have difference Wt1 minus Wt2 related to what? Related to the correlation of our psi. So it can be easily seen that now, due to the behavior of the Wiener process, let me recall you that at R3, Wiener process tends to infinity with probability 1. We get that this series tends to the remaining term without exponent, alpha A0, B0, which is exactly expectation. So we have this mixing property. And finally, one can conclude that our random node gamma t is a ergodic process. And we can calculate its asymptotic of its topological characteristic, just checking expectation of topological characteristics of gamma zero. And now is the time just to see that gamma zero is actually a random node and gamma 0 can have arbitrary topological. Let me do this. I will switch the files. Mhm, mhm, mhm. So here is our idea. We just have the smooth curve. In my case, this is in the picture it is a circle, but doesn't matter. We just map this smooth curve using our random field. And now we want to study the properties of the obtained random net. The first theorem is with probability 1, gamma has no point of self-intersection. The idea is the following. Let us consider two non-intersecting subintervals I and j of 0 to p, 2 pi. Then this expectation 1 over epsilon over 3 indicates that difference between eta t1 and eta t2 is less than epsilon, has a limit under epsilon tends to 0, and this limit is less than infinity. How one can check it? Very easily. Because this expression, indicator divided by epsilon in power 3, approach delta function. And we already discussed it with you that expectation of the delta function from the random vector is just density of this random vector in density of this random vector in the space now R3. And due to our expression for the covariance, now this covariance, this density have a denominator like gamma T2 minus gamma T gamma T T1, and here we have like 3 3 power. But let me recall you that it is not all density. Just well, let me recall you that I and j are non-intersecting. So gamma t2 minus gamma t1 is separated from 0 due to this integral, the limit of these integrals is finite. So we have such a simple conclusion, but this simple conclusion gives us a possibility to prove the statement, namely, now consider the random set the set A of such omega that there exists point of self-intersection for our random node. So that there exists point T1 from interval I, T2 from interval J, that eta T1 is equal eta T2. And it is not very hard to prove that A is a random event. Maybe you remember from course of probability theory that when we want to discuss probability of something, we firstly have to check that this something is a random event. To check this, we just consider opposite event and use continuity and rational numbers instead of T1, T2. After this, one can check some omega with this set random event A. Suppose that we have such point of intersection. Then what we will get? We will get T1 from the interval EI and T2 from the interval J, such that we have the point of intersection. Then it occurs that due to differentiability of our random curve eta, the total time which we spent near this point of self-intersection is none less than some constant, it is random of course, multiplied by epsilon square. It is trivial because we already have this picture. And you see these intervals where we have a point close to the point of self-intersection. You see that we spent the time, double time, I say dt ds, which is greater or equal than epsilon multiply epsilon in power 2. Since then, this limit, here I put the indicator of the event A, this limit is equal to plus infinity because the integral will be greater than some random constant multiplied by 1 over epsilon. So obtained contradiction proves the theorem. Our random node, we have really random node, obtained random curve, has no any points of self-intersection. Now, what about topological type? Node gamma can have various topological type. What do I mean? You know that there are different nodes which are non-homotopic, so they cannot be transformed one to another without cutting in some place. So one can ask, how complicated can be our random node? And the answer is following: as much as you want. So with positive probability, we can have a topological type of any complexity. How one can check this? Firstly, let me start from some recalling of the properties of Gaussian measures. I will consider the measure mu, which is a distribution of the first coordinate of our random node in the space of periodic function on continuous periodic function on C 0 to pi. Let me say that, firstly, this C with index P space of continuous periodic functions on 0 to pi is a good space. It is Banach separate space with respect to uniform node. Secondly, mu is a Gaussian measure here. Why a Gaussian? Because we suppose that psi1 is a Gaussian random field. So we have classical situation for infinite measure theory. It is a Gaussian measure in the Banach space. And it is well known that support of this Gaussian measure is linear subspace, closed linear subspace of this space. This is a well-known fact. And I'm claiming that this support is equal to the all space. This is a statement. Maybe you remember from the probability course that Gaussian random vector has linear support. It can be concentrated on some hyperplane in the space. It depends on the property of the covariance matrix to be non-degenerate. And if covariance matrix of the centered Gaussian vector is non-degenerated, then one can conclude that support of this Gaussian distribution is the all space. In infinitely dimensional case, we cannot state the same very easy, but one can proceed more or less in the same way. So we just take continuous functionals on this space CP 0 to pi and integrate it with our random field. If the statement of the lemma is not true, then it will be easy to find such continuous functional on the space CP that it kill our random process. Namely, now continuous functionals on the space of continuous periodic function is a measure. And it's this signed measure, of course, and it must satisfy this condition. But this means that for any u which belong to R2, we have the following, that just this phi u minus v, kappa du dv equals 0. What is the reason? Oh, okay, let me write. I just doing this one. I just consider psi, excuse me, psi 1 of u, multiply on this integral gamma 2. Here is psi 1 from v. Here is kappa, excuse me, there is no kappa dv, and then take an expectation. This equal to 0. The expectation must be equal to 0. But when we consider expectations of the product of two these things, we get exactly our covariance, which is, as far as I remember, norm of u minus v squared. That's all. So it is trivial, but a very, very efficient formula, because you see what we get by this formula. Let me discuss this slightly more detailedly. In this formula, we have integration of the product of two values. One is kappa, another one is phi, and we have phi u minus v kappa dv. This is a convolution. Yes, this is a convolution. Phi a convolution with kappa, at least in the sense of the distributions, Schwarz distribution theory in R2. So we conclude that convolution of our kappa, the signed measure, placed on the curve, initial curve, in our case, this is a circle, in R2, with the function phi is totally equal to 0. But it occurs that this is enough to conclude that kappa is equal to 0. Why? This is the way standard. We know that Fourier transform turns convolution into the usual product. Let's take Fourier transform of this convolution. It must be totally equal to 0. But you remember, phi capital is like Gaussian distribution. Its Fourier transform is not equal to 0 totally. So kappa with hat is equal to 0. And it means that kappa is 0. That's all. So we prove our lemma. The distribution of our Gaussian coordinates is has a support equal to the space of periodic function. Since Xi1, Xi2, Xi3 are equidistributed independent, then nodes of different complexity can be approximated. What I wrote here. Suppose that blue line is some node. I just wrote a simplest non-trivial node, trefoiled, and the black line is our random curve. As we discussed in the previous lemma, we can approximate, we can find epsilon tube near this trefoil, which is containing our random curve. From this point of view, one can say that maybe complexity of our obtained node is none less than the complexity of trefoils. And from other, here is not all the proof. From other point of view, you remember that we can approximate any curve, and the same remains to be true for the second derivative of Xi. And second derivative, if we control second derivative of Xi, then we can do this approximation, just avoiding additional knotting in the tube. And it means that we will get exactly trefoil, for example, in this case. So this is the idea of the proof, that we can get arbitrary complexity. Now let's see that we can change we can change topological type of our random. Why it is true? You remember that the covariance of between our coordinate values of our coordinates. Let me call you Xi1 U, Xi2 Xi1 V is E minus norm U minus V square. This is a function which is very rapidly decreases as infinity. And you remember that if we have two jointly Gaussian random variables, then if they are non-correlated, they are independent. So one can imagine that when the distance between U and V became to be great enough, these two random variables became to be almost independent. This is just non-mathematical, but good explanation of what happens. So if we have our initial curves placed far enough for one from another, then the image are almost independent random curves, so they can have different topological types with positive probability. This means that it changes its topological type during the motion. Moreover, as we have seen, the change cannot happen at the deterministic moment of the time, because at the deterministic moment of the time, we have no self-intersection with probability 1. The situation here is very interesting and looks like the behavior of the trajectories of the Brownian motion. Let me recall you the behavior of trajectories of the one-dimensional Brownian motion. So suppose this is a time, here this value of W, and then it looks like the following. Yeah. I just was trying to draw chaotic, very ugly function, which is now differentiable and so on. But let me say to you the following. If we take two values, T2 and T1, then of course, probability that W T2 is greater than 0, exactly as in my picture, and WT1 is less than 0, exactly as in my picture, is positive, yeah? It's trivial. Everybody knows the two-dimensional distribution of Brownian motion, and this conclusion is very trivial. But what does it mean? W has continuous trajectory. It means that somewhere here we have just a point where we intersect 0. But let me recall you that any t which is greater than 1, than 0, Wt is not equal to 0 with probability 1. So this t star must be random. This is a conclusion. Exactly the same happened with our random node. It changed topological time. A lot of times between two fixed points, moments of the time, but it changes in the random moments of the time. This is the explanation. Now let's go for the properties of this. Here is the picture, how it looks like during the motion. And now we can go to our to the properties. We already know that we have ergodic state theorem. Here is it. Here is it. So in order to understand asymptotic properties, geometric properties of our random node, we just need to understand geometric properties of the geometric topological properties of this random node at fixed moment of the time. For example, the 0 moment. Yeah. So start with very simple characterization. This is a length of the obtained random. Suppose that our initial gamma 0 has natural parameterization, so it has derivative which norm is equal to 0. We know, suppose that the initial characteristics of psi1 is a such covariance, then psi prime of u is a matrix. Psi is a random field, so psi prime must be matrix, which is independent from psi of u in the same point. By the way, this is a usual property for stationary random processes. Yeah, the derivative and value of stationary random processes at the same moment of the time are non-correlated. But for Gaussian case, it means that they are independent. This is just explanation why it happens. And moreover, in case of such covariance, it occurs that the psi prime of U consists of ID standard random variables. It is a nice conclusion, yeah? Now we can use a trick from quantum field theory. They like very much. People from those part of mathematics like very much such metrics which consist of independent standard Gaussians. And since for arbitrary orthogonal matrix psi prime U multiply on V is equidistributed with psi prime, one can conclude the following, that for all A which belong to R2, R3 expectation of the norm is equal to the norm. Here is expectation of the eta, where eta is a standard Gaussian random vector in R3. And this expectation can be calculated easily and is equal to multiply square root of the fraction 2 over pi. Since then, the average length of our gamma t is 2 square root of pi. From this point of view, we have interesting conclusion. You see, our random field psi is isotropic, but it occurs that it is slightly enlarged our gamma. Initially, we suppose that the norm of the derivative of f0 is equal to 1. So the total length is equal to 1, but we get the expectation which is greater than 1. Yeah, it is interesting. So now let us came to other characteristics. This can be a number of bridges over fixed plane. It is a valuable characteristic of complexity of the node. But in our case, we just slightly cheating because our bridges can be noted. At least at this moment, I cannot control that all these bridges are the really bridges without noting. Yeah, without noting. But nevertheless, let's try to calculate such characteristic. Consider a plane, and this plane cut our random node, and you see bridges over this plane. I think that it is not necessary to say what is bridge. It is very clear from the picture. But I just recall you that sum of bridge can be noted. Since for our random field is isotropic, it is enough to consider a plane which is parallel to some coordinate plane. This means, excuse me, so we consider only planes where the first coordinate is equal to fixed number. Then a number of bridges coincide with the number of upcrossing of the level A by the process psi1. Yeah, you see, the green lines is the bridges over the level A, and red points are the points of upcrossing. But for number of upcrossings, we have very nice Rice formula. Let me recall you. It is the following formula. Expectation of the number of upcrossings is equal to the following integral. Double integral over parametric set 0, 1, integral from 0 to plus infinity x qs ax, where qs is a joint density of psi1 and its derivative. And it is easy to imagine why we have such formula. The first argument in QS is equal to A, because we must be at the level A. And the second argument is just expectation of the value of derivative if it is positive. So it is very trivial to understand why it must be right. Of course, there are some technical moments to prove that it is right. So now this random element has random variables has the following distributions. They are independent. Yeah, we suppose that f0 has a derivative of the norm equal to 1. Since then, one can have the product of two standard Gaussian densities. And due to this, the number of bridges is the following. Expectation of the number of bridges is of the following kind. So it decreases very fast when we move away from 0. Now we already discussed that not only one can consider ergodic, we have a mixing property, and one can consider even central limit theorem for some characteristics. We already discussed that coefficient can be found, mixing coefficient, and this mixing coefficient is can be estimated by t plus 1 in minus 3 over 2. We discussed it in the beginning of my lecture, how to do this. Since this gamma, this integral from this mixing coefficient is less than infinity, then one can say that one can apply ergodic theorem and central limit theorem and whatever you want to asymptotics of our geometric characteristic, and it checked in the book of Adler and Taylor, Random Fields and Geometry, that for Gaussian random process with smooth characteristic covariance, such expectation here you see highest moment of the number of crossings. It is interesting because Rice formula actually is only for the first moment of the number of crossings, but it can be modified in order to get such kind of expectation. And it was done in those book. And together with the statement that the mixing coefficient is less than 1, than infinity, one can conclude that one can apply central limit theorem. So one can conclude that square root 1 of square root of this number of bridges minus its expectation, which we already calculated, and normed by 1 of square root of t, tends to some Gaussian limit in distribution. Here, the central limit theorem for stationary random process obtained by Ibrahimov and Linnik was used. So let me recall you that we obtain the following: that expectation of the number of bridges of our random knot over the plane on the level A decreases fastly, namely as e in minus a squared 2. So it seems that with a great probability, gamma t is almost flat. So what is the shape? In order to understand this, one can introduce Möbius energy. And this is a Möbius energy of the any knot, any closed smooth curve this energy can be calculated as a double integral from such difference, where we have the two terms. The first one contains the usual Euclid distance between the points of the curve. The second one contains the distance along the curve. Here is a picture. The red line is the usual Euclid geodesic, and green line is a geodesic on the curve. It is trivial that it is bigger, so the difference is positive. It is well known. It is well known that due to the due to its formula, Möbius energy does not depend on the parameterization. It does not change under affine transformation, affine transformations of our node. It does not change of the inversion with respect to some circle, and minimal value of the Möbius energy is achieved on the circle and equals 4. And it occurs that energy and average quotient number are very related. So if we consider the projection of our node onto any plane, and for any projection, we calculate the number of quotient points. On the picture, there are 4 such points. This number will depend on the normal vector theta to our plane. And the average quotient number is the following. Here is the integral over the sphere over all these normal vectors theta. So we take uniform distribution on the sphere and integrate this number of points of self-intersection of the projection. The obtained value is called average quotient number, and it occurs that for average quotient number, we have a Gauss formula, like you see on the picture, and we can consider minimal quotient number. So to find such minimal from number of points of self-intersection, just varying theta over all units phi. It occurs that this minimal quotient number is a topological invariant, and there exists estimation which is which connects the Möbius energy with the minimal quotient number. As a consequence, the number of different types of nodes where energy is bounded is more or less than is not greater than such interesting value. Yeah. And finally, to do the estimation of the Möbius energy, we have to check this one. And actually, one can see that what we will have here. We have a moment of the, in our case, moment of the Gaussian random process, norm of the Gaussian random element in space of continuous periodic functions, yeah. And there are a lot of such estimation. For example, it can be estimated by the distribution, standard Gaussian distribution, because f prime now is related again to the matrix with standard Gaussian variables. So one can check that Möbius energy has exponential tails. And from this point of view, we see that complexity of our nodes decreases very fast, has a distribution which decreases very fast. So it can be very complicated with large probability. So one can estimate probability of our node to be to have different complicated topological kind. That's all what I wanted to present in my lectures for this school. Let me summarize. We start with you with understanding that what we need from the model of the random node. We need the possibility to estimate some shape of the random node. We need the possibility for a random node to change its topological type to have a dynamics. We consider statistical approach based on the free polymer model, where we start from the random walk or inner process. Discuss the Flory numbers for such polymer models. Obtain the problem related to self-intersection of the planar Wiener processes. We discussed how to overcome this difficulty to produce renormalized self-intersection local time. And it occurs that this self-intersection local time became to be some geometric characteristic of the planar Brownian motion, or moreover, planar integrator. After this, we began to construct random node as an image under the smooth random mapping of smooth curve. And it occurs that we are able to do this and obtain the random node which changes its topological type and has a characteristic which can be estimated and about which we can say something about its distribution. That's all what I want to present, and thank you for your attention. Maybe somebody have questions or comments, please. Okay, if